there's not any friction here on the incline, okay? So we'll assume we're on Earth and we're on a frictionless incline. Are there any other forces that are acting on that? There are not. So I have weight force down. I have the normal on an incline. And then I have tension. You have two options. One option, because I don't like the way that this is, I want to break it up into components. I want to show all of them at least having similar axes, or what component would go in the X and what component would go in the Y. So you have an option. I can leave it like this, and I could think about my X and Y axes just as normal. So if that's the case, tension has to be broken up into components. The normal force has to be broken up into components according to theta, okay? Or I could break my axes up along tension and along, oh, that was terrible, along tension and along the normal force. So I'm going to just kind of skew the axes. So now tension is along the X, the normal is along the Y, and the only force that's not on an axis is going to be the weight force. So I could break that up into components. So maybe there's my axes. So I can see that the X component of the weight force is going to interact with tension, and then the Y component of the weight force is going to interact with the normal force, okay? I prefer this method for you to try to rotate your axes just a little bit, or to skew them, instead of making, this is going to be easier. I'm dealing with one set of components versus two sets of components. And plus, sometimes the math on this is going to get much more difficult versus the math on this. So I recommend doing it this way, but again, it's your call. Okay, so at this point, I have a free body diagram worksheet for you, and if Brooke would pass that out, that would be amazing. So let me give you, like, I don't know, take 10, 15 minutes. There's a front and a back. And I want you to draw the free body diagram for whatever it tells you to do for that particular object. And then I want you to get together as a class and go over them all and decide what you, if people are right, if people are wrong, what misconceptions are happening, and then let me know what's happening. If there's one that you're like super stuck on, make a video, post it for me, and I'll look at it while I'm in that Google conference, okay? So do that now. I'm going to keep going after you get this done. I still have just like a few more slides that I want us to do, because I think we have time to just get through a couple of Newton's second law problem examples, okay? So you can stop the video now, so that way you can pass out the worksheet, but I'm going to keep going because we're going to keep learning just for a little bit longer, okay? Okay, so when we're solving any type of Newton's second law problem, it could be an equilibrium problem, it could be a free particle problem. These are the things, or this is kind of, I think, a really easy way for us to set up a problem when we're giving something with forces. So, sketch and label some kind of diagram, draw a picture. Tell me what's happening to the object. So before you draw a free body diagram, sometimes it helps to just draw a picture first so you can visualize the entire situation. When you've done that, think about all of the forces that are acting on an object, and then draw your free body diagram, okay? So identify all forces that act on the object and draw the free body diagram. So sketch something first, visualize the situation, figure out all the forces that are acting, identify all the forces by drawing a free body diagram. So let's do an example of just seeing how forces can go into components, and then maybe what I can ask you. This is, again, more on the simpler side of these type of problems. This says a block of mass 0.50 kilograms travels with a speed of 2 meters per second in the positive x direction on a flat frictionless surface. So here's my 0.5 kilogram mass, travels at a speed of 2 meters per second in the positive x direction on a flat frictionless surface. It says on passing through the origin, the block experiences a constant force of 3 newtons at an angle of 60 degrees. So it was traveling, maybe it was just traveling horizontally through the origin, and now all of a sudden it's going to experience a force at 60 degrees, and that force is specifically 3 newtons. It says, what are the accelerations of the x and the y components? So they gave me a picture here, which is helpful. I don't have to visualize a picture, but it does help me when I draw my free body diagram, which they kind of already did for you. Here's my particle moving through the origin, and I know it has a weight force. I know that it has, if it's acting with the normal force, or if it's moving on a surface, then I know it has the normal force. But I just want to focus on that constant force of 3 newtons right now. So for right now, I'm just focusing on that applied force. We already know that that's 3 newtons, and it was at an angle of 60 degrees. Okay, my goal was to find acceleration in the x and an acceleration in the y. That was my goal. So first of all, I could find the force. So this is my y, there's my x. I have an angle, I have the hypotenuse. We could find x and y just by using trig. So I could do, I know that sine 60 is going to be equal to y over 3 newtons. And then I could say the same thing for x, because then I know cosine 60 is going to be equal to x over 3 newtons. So then I would know the force component in the x, I would know the force component in the y. So what, sine 60 times 3, 2.6? And then cosine 60 times 3 then would be 1.5. Okay, so I know the force in the x, I know the force in the y. My goal is to find acceleration in the x and acceleration in the y. So I can do that because they gave me the mass. And they told me the mass of that block was 0.5 kilograms. So I could do x first. And I know that the x force, because I know force is equal to mass times acceleration. So the force in the x direction is equal to mass times the acceleration in the x direction. So 1.50 newtons equals, actually, let's not do that. Let's rearrange this for acceleration in the x. Fx divided by mass will give me acceleration in the x. So then I know 1.50 newtons over 0.50 kilograms. So a sub x has to be equal then to 3 meters per second squared. So I know a sub x is equal to 3 meters per second squared. Let's do the same thing for a sub y, except this, instead of being 1.5 newtons, would be 2.60 newtons divided by 0.5, which would then give me a sub y to be 5.2 meters per second squared. Okay, so I've answered the question in that I found the force components in the x, the force component in the y, and then I knew the mass, so I could find the acceleration in the x and in the y, okay? So that one, again, is on the easier side of problems. Let's see another one. Okay, a hockey puck having a mass of 0.30 kilograms slides on the frictionless horizontal surface of an ice rink. 2 hockey sticks strike the puck simultaneously, exerting the forces on the puck. The force F1 has a magnitude of 5 newtons, and it's directed at 20 degrees below the axis. So we should be drawing a picture right now of the situation. The force F2 has a magnitude of 8 newtons, and its direction is 60 degrees above the x-axis. Determine both the magnitude and the direction of the puck's acceleration. Okay, so let's draw a picture. And in